In the last lecture, we had introduced what we called as the BB84 protocol for a communication to be set up between Alice and Bob, and what we had said was the following, that both Alice and Bob have decided to have a protocol in which the coding and decoding of polarized light will happen by using a pair of bases for both encoding and for decoding. One of them we called as the horizontal vertical basis, and the other one we called as the diagonal, or what we have been calling as the plus minus basis. Now based on that, we had said that randomly a particular basis is selected by Alice to encode a particular bit, and as a result, when Bob receives it, assuming that there are no eavesdropper in the channel, whenever their bases agree, because Bob would also measure it randomly, whatever bits Alice sent would be also received by Bob. In addition, in the remaining cases, 50% of the cases, where their bases of sending and receiving do not agree, they would also probabilistically agree for 50% of the time. So as a result, in case where there are no eavesdropper, the bits sent by Alice would agree with bits received by Bob total 75% of the time. However, at that stage, Alice makes an announcement of what basis she used in sending the sequence. Now, on hearing that over a public channel, Bob will remove all those bits where their bases do not agree. This would also result in half of those where their bases did not agree, but Bob received the same bits as Alice sent, to be also discarded. So in other words, instead of agreement being full 75%, the agreement that they have arrived at is a perfect 50%. Remember, the 75% was only a probabilistic estimate. So coming back to the picture that I gave you, we had shown that when Alice is using these bases, this was there in the slide, but when Alice is using these bases and Bob is using these were the bits that are sent by Alice, and let us suppose these are the bases that are used by Bob. We simply identified those where their bases agreed. These would be discarded in any case. Now let us see what happens if there is an intruder in the channel. So I have now put in the presence of a Eve, which I will put in between, because she will have to interrupt the process of sending briefly and then measure it herself. Not knowing what basis was used by either Alice or Bob, Eve also decides to do a random job. So she will toss a coin and also send a sequence, but on the other hand, let us assume that her bases are these: plus, horizontal, vertical, horizontal, vertical. It's just a random sequence which you can work out. Now let us look at what happens here. Now at this stage, before the bit reaches Bob, if Alice and Eve's bases agree, then the bit received by Eve would be the same as that sent by Alice, and so therefore this bit will agree, and here this bit will also agree, this bit will agree, this will agree, and these will have no agreement. Now even though they don't have agreement, one would expect that 50% of the time there would still be an agreement between Alice and Eve, and let us say that Eve measured 0 here again a 0 there, and let us suppose these were Eve's measurement. So you notice these are the cases where there were agreements in spite of the fact that their bases did not agree. Now let us look at what is happening. Now Bob would receive something. Now what Bob would receive would depend upon whether all the three bases are the same. Now in cases the three bases are the same, Bob would receive exactly what Alice sent. So therefore, let me write down here 1, let me put a double tick on it to show that everything has agreed there. This is another case like that. Well, we don't have any other case. So therefore, these two agree. Bob will receive random things here. So let me write down what those things are. Let us say 0, 0, 0, say 1, 1, 1. Now look at what is happening here. The situation is the following, that out of these cases that we have, 1/4 of the cases, Bob's basis, Eve's basis and Alice's basis are identical. Now previously, in the absence of Eve, only 50% of the cases, the Alice's and Bob's results would match perfectly. Another 25% was probabilistically, which we would throw out in either case. So what happens here is this, that the probability now drops to 25%, where Alice, Bob and Eve, their bases agree, then only whatever Alice sent, Bob would receive. There would be cases of 25% where even though Alice and Bob's bases do not agree, Bob will not receive those because of the interruption. Now how does one take care of this? So what happens in that case is this, that the protocol works like this. To start with, Alice will choose, let us say 4n plus delta number of bits, and encode them randomly, as we have said, using a toss, and then send them to Bob. Now Bob also will measure them using another set of random bases. Then, as we have said, Alice would announce over a public channel the sequence of bases she used to transmit them. But remember, she never announced what bits she actually transmitted. Now, so what will now happen is this, that we have taken 4n plus delta. So at least in 2n cases, their bases would agree, because we had said that the probability that they have used the same basis is 50%, but 50% doesn't mean out of 4n you exactly agree in 2n cases. So we have taken some extra bits to make sure that the agreement is at least in 2n cases. And we have said the Bob will discard all those where the basis used by Alice was not the same as the basis used by him. Now what happens is that Alice and Bob have a set of bits, the number is 2n, and in ideal case where there is no Eve, the bit sent by Alice and the bit received by Bob must agree. So at this stage, what Alice does is this, she picks up a random sequence of n bits out of that. Remember, I started with 4n plus delta, we now have at least 2n. Out of that, Alice chooses a random sequence of n bits, and this time over a public channel she actually makes the announcement that in sequence number 5 I sent 0, in 7th position I sent 1, or whatever you have. Now this is public. So we still have n of them which are still confidential out of 4n plus delta. Now Bob makes a comparison now of what Alice sent and what he received. Now remember, we are talking about situation where the bases used by Alice and the Bob are identical. So therefore, ideally they should get the same bits. But on comparison, if Bob finds that the agreement is not within acceptable error of a noisy channel, then they know that something is going wrong. In all likelihood, there is an eavesdropper in the channel who is disturbing the system. And if the disturbance is intolerable, then they will simply abandon the protocol and would wait for an opportune time, assuming that Eve could not be listening to the whole process forever and to restart the dialogue. Now, once they are sure that there is an agreement between the bits which have been publicly announced within tolerable error, then they can use it, the n bits which have not been announced, as a one-time pad. Okay, that's it. But on the other hand, there are other informations to be taken care of. At that stage, what they will do will be two different processes. They will follow up their agreement of the secret n bits with what we call as the information reconciliation. And finally, they would do what is called a privacy amplification before going ahead with the protocol. Now let me explain what these two things mean. I will not go into the details, but let's look at that. Information reconciliation is actually a process of error correction applied on the keys with Alice and Bob to ensure that they have identical keys. Okay? Now, when you do that, they will be required, or of necessity they will be revealing a little more information. However, this extra information revealed to Eve can be shown not to matter much. Now, what do? See, they do it by a process called cascading. So they have a set of n strings which ideally should agree completely. So they divide this entire key string into blocks which they have agreed what should be the size of the block. And then they do a parity check on each block. What is a parity check? They simply add up modulo 2 the bits that is there in a given block and announce that these are the parities. Now remember, we are not talking about announcing the actual bits. You are simply saying, supposing there are 1000 bits there, we have added them, we are saying this should be a 0. Now Bob's parity check must agree with the parity announced by Alice if they had identical sequence. Now, assuming that the error possibility is small now, of course this is still possible that the parities agree, but there are still errors there. But once you have done that, okay, you take those blocks for which there are errors identified. Now either you can abandon them, or what you can do is you can subdivide them. Now once you subdivide the blocks into sub-blocks and carry on the parity check, then discard those blocks where you know that definitely there are errors and they are small enough to throw it away. So in the process, as we have said, they have given some information to Eve, but on the other hand, it doesn't actually amount to much. And after this, there is this whole thing of privacy amplification. Now this is the idea behind the privacy amplification is this. So what Alice, now that the reconciliation is there, ideally we have a set of strings between Alice and Bob which are identical. Now Alice randomly picks up a subset of these strings which she shares with Bob. Now what they do is, they now do a parity check on these, or calculate the parity of these blocks, which now they know are the same, because there are no errors have been eliminated. Now the parity they calculate in the various blocks, now they become their secret key instead of the strings that was already set. This is the principle of privacy amplification. So this is roughly what BB84 protocol says. However, it turns out that BB84 protocol is not all that secure a process in spite of all that we have said, because our assumption has been that Eve uses randomly the same set of bases as Alice and Bob use for doing her measurement when she interrupts. It can be shown that there are bases in which Eve can make a measurement which will make a much bigger difference to this whole process, and she can get a huge amount of information by using such bases. We will not have time to discuss it, but we will do those in one of the assignments that we will give along with this course. Having discussed BB84 protocol, we focus our attention on alternative protocols that are there. One of them is known as a B92 protocol, and the B92 protocol works like this. In this case, Alice encodes her bits in a predetermined manner. Remember, in BB84 protocol, she had encoded them by basis which she decided on the basis of a random coin toss, but she doesn't do that. What she does is, supposing she wants to encode bit 0, she will use a computational basis and encode this bit 0 as the state 0 itself. So this is, I will call it A equal to 0, Alice's bit. Now if she wants to encode a bit 1, she will not use the vertical basis, this was horizontal, as was used in the previous case, but she will use the diagonal basis and code it as 0 plus 1 by square root of 2, namely as plus, and this is the bit 0. So these are predetermined. Now what Bob has is the following. This is shown in this picture. If you look at the slide, the left hand side picture shows the encoding that Alice does. Now Bob has a set of bases, 4 bases, which we have written down: 0, 1, 0 prime and 1 prime. Now look at these a little carefully. So the Bob 0 is parallel to Alice's 0. But you notice one thing, that Bob has the other basis. There is a 0 prime there, which Bob has used, which is parallel to Alice's 1, which is encoded as a diagonal basis. And perpendicular to these two pair are the other 2 bases of Bob. So what Bob does is this. Bob uses a coin toss and decide which basis he will use for measurement. Now remember, in this picture, 0, 1 is the computational basis for Bob, and 0 prime, 1 prime is the diagonal basis for Bob. So based on a coin toss, Bob will use either a horizontal vertical basis or a diagonal basis. Now let us look at what happens if Alice let's look at the first case. Suppose Bob used computational basis to measure. Okay. Now Bob in the computational basis could measure either 0 or 1. So let us look at the picture again. Now if in the computational basis, which is 0 and 1, suppose Bob measures 1. Now notice, in that case, Alice could not have used, or Alice could not have sent 0, because in this particular case, Alice's basis and Bob's basis were identical. And since the bit 0 is perpendicular to the bit 1 in this basis, when Bob measured 1, Alice could not have sent 0. So she must have sent 1 prime. In the second case, suppose the basis that Bob has chosen is diagonal, and Bob measures 1 again. Now again, if you look at the picture, in the diagonal basis, which is shown by blue lines in this picture, supposing Bob measures 1. Now if Bob measures 1, Alice could not have sent 1 prime, because this is perpendicular to that. The 1 prime here is perpendicular to the 1 prime there. So therefore, Alice must have sent a 0. So therefore, now notice, in either case, if Bob measures 0, or well, in both cases, if Bob measures 0, no conclusion can be reached. So what happens now is this, that we have a definite conclusion if Bob measures 1. Now when Bob measures 1, they decide the final keys will be the basis which both used in their measurement, okay, for which Bob measured 1. In other words, the original bits are not the keys. Alice's A corresponds to Bob's A prime minus 1, and that becomes your secret key. So that is the content of B92 protocol. Before we conclude, we are going to talk about one more protocol, and that is what is known as the Eckert protocol. The Eckert protocol uses an EPR pair. The EPR pair will be used to detect the presence of an Eve in the system. In this case, Alice does not prepare her bits, but instead a third person, Charlie, prepares the bit, and see, he prepares it as an EPR pair. And having prepared it, for example, as 0, 1 minus 1, 0, he sends one qubit, the first qubit, to Alice, which is marked in the state with an A, and the second qubit to B. We have discussed this state in detail in many of our lectures. So here, our 0, as we know, corresponds to spin up, and 1 corresponds to spin down of a spin up particle. Now what will happen is this: Alice and Bob will use 3 coplanar axes to measure the spin of the particle. Now let's look at what happens here. So these are the coplanar axes that we have. I have indicated these axes by A1, A2 and A3, and B1, B2 and B3. Now let's look at what it actually means. Now notice, in this case, there are 2 compatible axes. So one of them is A2 there and B1 there. The second one is B2, A3 in one and B2 in the other. So these are compatible bases in the sense that suppose Alice generates using one of these bases 0 0 1 1 0 1 0 1 1 1. The Bob will measure the complementary string, and you can see why. See, supposing Alice used, we are talking about a pair, let us say A2 B1. So look at A2, which is shown there, and B1 is shown there. Okay. So in this case, what happens is this, that whatever Alice sends, Bob will measure the complementary bit. Now that still leaves us with 4 pairs, A1 B1, A1 B3, A3 B1 and A3 B3. Now these 4 are going to be used to detect the presence of Eve. How does one do it? Recall our EPR Bell inequalities. So suppose Eve does not interfere, then of course whatever you have said is true. But suppose there is an interference by Eve and Eve makes a measurement. What she actually does is to introduce an element of reality into the measurement. We define a quantity S as is shown here in the slide, where E stands for expectation value that each one has measured, using those axes. We have seen that if you had a local realism, these expectation value, the modulus of it, would satisfy what we called as the CHSH inequality, and it should have been less than or equal to 2. On the other hand, because we are talking about quantum states, in the absence of an element of reality, we have seen that this quantity for the state that has been given should have been 2 times square root of 2. So in other words, these bases where there is no agreement, Alice or Bob, they will use for determining if there is an Eve in the system by simply calculating these expectation values and find out whether CHS inequality is satisfied or not. If it is satisfied, then it means that there is an Eve in the system. Now with this we come to the conclusion of the subject of, or conclusion of our discussion of the subject of cryptography. We have discussed in detail the BB84 protocol for its simplicity. We have not talked about various attacks that Eve can make to make some of these arguments untenable. That's because the cryptography by itself is a fairly elaborate subject. We have seen B92 protocol, which is another variant of the same process, much simpler, but it turns out to be much more robust than BB84 protocol. And we have also seen a method of determining if there is an eavesdropper in the system by using our ideas of EPR pairs. That would give us an idea of what quantum cryptography is all about.